let's take a look at kind of the classic king of the related rates problems. And this one is trickier than the ones we've dealt with so far, and you'll see why pretty quickly, I think. All right, so what we have now is we have a cone with a diameter of 10 inches and a height of 15 inches. Water is being poured into the cone so that the height of the water level is changing at a rate of 1.2 inches per second. At the instant when the radius of the exposed surface area of the water is 2 inches, at what rate is the volume of the water changing? All right, so looking at this, it looks a lot like the kind of problems we've had before. Maybe it's got a couple extra numbers, but you might not see what's tricky about it yet. So let's start solving the problem the way we have before, and once we run into trouble, we'll stop. So what are the variables involved in this problem? What's changing as we pour water into the cone? Well, the volume is changing. The height of the water is changing. And there's another thing that's changing as water is being poured into the thing, and R is the radius of the water that's being poured in. The radius of the top of the water, the surface of the water is changing because that circle is getting bigger and bigger as the water fills the cone. And nothing is remaining constant in this problem. So this is a little bit different from the last problem where we had a cylinder and the radius was staying constant, but this time the radius is changing. So this is going to make our lives a little bit more interesting. So what are the rates that are given and the rate that we wish to find? All right, so right now what we have is we are given that the height of the water level is changing at a rate of 1.2 inches per second. So how do we write that? Well, we've got the dH dt is equal to positive or negative? Positive 1.2 because the water level is rising. And we want to calculate the rate of change of the volume of water. We want to calculate the rate of change of volume of water when the radius of the exposed surface area of the water is 2 inches. So when the radius is equal to 2, we want to know dV dt. Maybe one thing that'll make our lives easier right here is we're given the diameter of the cone and everything else is going to be in terms of radius. So why don't we just switch this fact to radius is equal to 5 inches. Okay. So we want to write an equation, often a geometric formula or trig equation, that ties all of our things together. So we've got the volume, the height, and the radius of a cone. And so our equation is V is equal to 1/3 pi r squared h. Okay, so this is the equation we're dealing with, and now we gotta keep in mind this italicized thing that we have kind of skipped over up until this point. How many variables do we have here? We have v changing, we have r changing, and we have h changing, but we only have one rate. So, how are we going to deal with this? If I implicitly differentiated this, I would have a dv dt, a dh dt, and a dr dt. But I only know dh dt, so I can't solve for dv dt because I would need to know dr dt in order for that to happen. So let's pull back, and here's what I'm going to do. I am going to pull out this thing that I never get to use, which is my cone with a hole in it that I can pour water into. So let's imagine that this was the cone that we were filling water into. And I've got colored water here, so it's a little bit easier to see. And I want you to tell me some things about the water that's in the cone in relation to the cone itself. So what do you tell about the shape that the water takes? And can you be specific about it? Well, here's the two key things I need you to understand here. That first of all, the shape that the water is taking is itself a cone. And the second is that the cone of water is similar to the cone that the water is being held in, right? This is the same basic relation of height to radius of the plastic cone as the water cone. They've got the same ratio of height to radius because the water is filling the cone that it is placed in. All right, so let's come back to the problem and we'll see how we need to think about this extra cylinder thing. All right, so the cone that the water is being filled in has a radius of 5 and a height of 15. So we've got this constant, the constant that's happening here is that the height of the cone of water is always 3 times the radius of the cone of water, because this is the cone that it's filling. Okay, this is the thing that makes cone problems in related rates tricky. So hopefully pause the video and go back and look at that cone being filled up with water again until you kind of get this idea. So what we can do is we can take this relation between H and R and use it to eliminate a variable in this volume for this specific cone that we're finding the volume of. Which variable do we want to get rid of here? Do we want to get rid of R or do we want to get rid of H? Well, we're given dH dt, so I would prefer to get rid of R here and have an equation between V and H. So in order to do that, I'm going to say that radius is 1/3 of height, or H over 3. And now I can substitute that in down here. So I've got 1/3 pi times H over 3 squared times H. All right, and so that's H squared over 9. So I'm going to combine the 1/3 and the 1/9 over here, and I'm going to have 1 over 27 times pi times H squared times H, which is H cubed. So now I've got a relation between the volume of the cone and the height of the cone at any moment as I'm pouring water into the cone. So I can implicitly differentiate this equation with respect to time, and notice how now I've only got 2 variables. So the fact that I have 1 rate means I'm not going to have any trouble solving for the missing rate. I've got dV dt is equal to 1/27th pi, that's my constant, pi over 27 times the derivative of h cubed, which is 3h squared dH dt. And so that's equal to pi over 3 goes into 27 9 times. H squared dH dt is what dV dt is equal to. All right, and now I can almost solve that. So to figure out dV dt when dH dt is 1.2, I'm going to substitute 1.2 in for dH dt. So dV dt is equal to pi over 9 times something squared times 1.2. And now I've got to find out what H is at the specific moment that I care about. So at the specific moment that I care about, I'm told that the radius is 2. But I need to know the height. What's the height equal to when the radius is equal to 2? Well, I've still got this relationship that the height is equal to 3 times the radius. So when the radius is equal to 2, the height is equal to 3 times 2, which is equal to 6. So pi over 9 times 6 squared times the constant rate of change of the height. And so that's equal to 36 times pi over 9 times 1.2. And so 9 goes into 36 4 times. And so that's equal to 4.8 times pi dV dt. And what's our units going to be for that 4.8 pi? This is talking about the change in volume over time. So volume is measured in cubic units of measurement. Our units of measurement here is inches, and our unit of time is seconds. So the change in volume over time is going to be 4.8 pi cubic inches per second for our answer. Okay? So that was kind of a lot. And the reason that it was a lot is because when you're dealing with cones, you've got to think about the fact that even though radius and height are both changing, they're changing in a specific relationship to each other. And so that specific relationship can be used to take one variable out of the equation when you're calculating the volume of a specific cone being filled with water. This is, I think, probably the hardest kind of related rates problem you'll see is one dealing with cones. We're going to come up with some extra problems by the time we get to the end of this worksheet, but this is the one where you kind of have to suss out the missing variable yourself when you're dealing with cones. So come back to this when you're dealing with a cone problem, and hopefully you'll be able to get through it.